Let's talk about data loss prevention, or DLP, and there's a few things to keep in mind here. What we basically want to do is reduce the amount of personal data and sensitive data that leaves our network and make sure that that data is not stored in places on the network that it does not need to be stored. So we're talking about things like data in use. So we want to control data on endpoint devices, laptops, mobile devices, and so forth. We have data at rest. So the DLP systems will then discover sensitive data stored in repos, right, repositories on our network, databases, network stores, and so forth. We're talking about data in motion. So we will monitor, detect, and block, or at least report on sensitive data that's being sent via email, as an example. And again, this can take place also over the network between endpoints on the network. So we're going to monitor and detect and then enforce encryption and or at least report on that data being sent outside of the network. So as I mentioned, as our networks continue to grow, data is just increasing exponentially year over year. So data in a vacuum without context is extremely difficult to interpret and understand exactly what data is valuable and of course what is noise. So an analyst is potentially faced with a lot of information inroads. Most organizations will have alerts, logs, feeds, and configs. But depending upon your industry, depending upon your job and what you're doing, it could also be forensics and information from the dark web, especially if we're doing threat intelligence analysis or trying to enrich our data feeds. So we're getting information from lots of different places. So we need a way to aggregate all of this data and actually feed it down so that we can search for bugs and we can search for the tools that the adversaries are using. And by doing so, we can categorize that data and enrich the alerts, as I mentioned, to track, to target, and to deter or prevent attacks. All right, so let's take a look at an IDP example. So here we have good old Alice, and Alice is a bit lonely today. Bob is not around. I'm not sure where he's at. He's probably getting scammed by some internet hacker right now via social engineering, knowing Bob. But anyway, we'll focus on Alice today. And so Alice wants to log into a ticketing application. And let's say it's a ticketing application for her work, and it is perhaps cloud-based or uses an IDP or an identity provider. So she's going to attempt to access that application. Is going to realize that she's not currently signed on. So what it does is it then goes out to an SSO provider or a single sign-on provider, and it will issue a request and say, hey, can you let me in? Well, the single sign-on provider also realizes, hey, she's not logged in. I can't authenticate her yet. So it's going to prompt her to log into that application. It will then send her an SMS code, right? A username and password along with an SMS code. So it's going to be a two-factor authentication. Once Alice provides that information, it sends it back to the SSO provider, who then will query an IDP. It'll issue what's called a SAML request to the IDP. So a SAML request is a security assertion markup language, and it's a standardized way to tell external applications and services that a user is who they say they are. Right? It doesn't authorize, but it authenticates. So it sends that SAML request to the IDP. The IDP will then authenticate, send that SAML response back to the SSO provider or the single sign-on provider, who in turn then sends that SAML assertion back to the ticketing application and saying, yes, Alice is who she says she is. Go ahead and let her log in to the application. Okay, next, let's talk about email security and a few things I want you to be familiar with. We have the concept of DMARC, DKIM, and SPF. So DMARC standing for Domain-Based Message Authentication, Reporting, and Conformance, right? That's a mouthful. SPF is Sender Policy Framework, and DKIM is Domain Keys Identified Mail. So we'll talk about each of these in just a second. So the gist of what these things are designed to do is basically reduce spam and spoofing, and basically hackers using email to launch attacks on various organizations, and also give organizations an idea of how their emails or their email domains are being utilized, if they're being hacked, spoofed, and so forth. So if a sender wants to implement DMARC, DKIM, and SPF, they will initially log into their DNS server, and they'll publish a few records. They'll publish the SPIF, a DKIM, and DMARC records into DNS, which basically specifies what IP addresses can emails originate from. It will also validate the header information from an email, so the sender will actually publish their public key in the DNS record. And then every time an email gets sent from that sender, they will sign that message with their private key. It's in the header field of their email message. So that way the recipient can then check DNS and verify via the public key that the sender is who they say they are. Okay, so let's walk through this. So the sender sends an email. So he sends it to his email server. His email server then sends it over to a receiving email server. That receiving email server then will check DNS to see if there is a DKIM and an SPF policy in place. And it will also test to see if those things pass or fail. Now, DMARC kind of ties all these things together. Again, the originating organization, their DNS server will publish a DMARC policy. The receiving email server queries DNS and sees what that DMARC policy is. It can either be accept, if that email is validated, go ahead and deliver. In other words, our policy equals none. We can set it to quarantine, So if it fails those checks, those DKIM and SPF checks, then we can place it into a junk or a spam folder. Or we can say, no way, if it actually fails, don't even deliver it, just drop it, mark it as undelivered, don't deliver it to the recipient at all. And then we can also send reports back to the originating email sender to let them know how their domain is actually being utilized. We can send an aggregate report that just shows everything that comes through, and we can also show a failure report or a forensics report so they can see how often their email domain is being spoofed or spammed. Now, the recommendations are when you very first set these things up, set the policy to none for a period of time so you have an opportunity to tune things, because if you set it to reject right off the bat, you may have things not tuned properly and your emails won't be delivered. So it's definitely recommended to be a phased-in approach. We have the surface web, which is pretty much what we're used to, the deep web, and then the dark web. So the surface web are publicly accessible websites that are indexed by search engines like Google, Bing, Wikipedia, Reddit, so on and so forth, right? Publicly accessible websites that people visit on a daily basis. They're also available, or accessible rather, via standard web browsers. That actually comprises about 5% of what's available on the internet. So that's why I have the picture of the iceberg here. Now, if we dig down below the surface, then we come up with the deep web. And the deep web is cloud storage, email inboxes, it could be legal documents, research articles, financial records, and so forth. So basically, documents that are not indexed, they are protected by some type of authentication mechanism, passwords, maybe a paywall, and then various security measures like firewalls and so forth are put in place. Although you can get to them with a typical web browser, they're not indexed and they're not searchable. And then below that, we have the dark web, which is what I talked about just a moment ago. So these things are not searchable, they're not indexed, and they're not even reachable by normal web browsers. So they're .onion sites, so they don't show up in any search engines, and you need specialized software to actually access these sites. And the tools that you use encrypts and anonymizes traffic. So it requires specialized software like the Tor browser. So just a bit more about the Onion router or Tor and the Onion routing network. So this was actually originally created in the mid-90s by the U.S. Naval Research Laboratory to help secure U.S. intelligence communications online. So without going into too much detail, let's just take a quick look at how this works. So here we have a user who actually wants to get to a destination. And again, this is a destination that's on the dark web. So it's a .onion website. You can also use this to access surface web websites. So it doesn't have to necessarily be just dark web. You can use the Tor browser and the Onion routing network to access publicly accessible websites just like you would today. It basically anonymizes your traffic, and this comes into play with like journalists, or if you're in a part of the world that has heavy censorship, then the Tor browser can be of benefit to you. But again, in between the user and the destination is the Tor network. And then within that network, there are thousands of nodes. A lot of folks will volunteer their computers as middle nodes or entry or exit nodes on that network. So a user using their Tor browser will connect to the Tor network, and they'll go through typically 3 nodes to get from point A to point B. Each node in the process only knows of where it came from previously, one hop before, and where it's going to one hop next. So the nodes in between don't know where that traffic originated from or where it's actually ending up. So the user will connect, it goes into an entry node. The entry node then decides where to send it across one or more middle nodes until it reaches an exit node and then goes out to the destination. Now you'll notice that the blue lines here are encrypted communications that's encrypted by Tor. Once it hits an exit node, it is unencrypted and sent on to the destination. However, the destination does not know the originating source of that data. The only thing it knows about is the exit node. So the communication, when it goes back to the user, follows that same path. It basically creates a circuit. It goes back the same path, and the user will take that path until that communication is done, or they decide to create a new circuit, in which case it will spin up a different pathway.